This is Kevin Cole. The topic is thermodynamics, and the example is Joule at the waterfall. James Joule studied the mechanical equivalent of heat. He struggled to explain his work to others because it was different from the caloric theory, which was the prevailing theory. Joule posited that a waterfall would be warmer at the bottom as potential energy is converted to heat. We're going to treat the water traversing Niagara Falls as a closed system, and we're going to find the change in energy, E2 minus E1 in joules, and we're going to find the change in specific internal energy, little u2 minus little u1 in joules per kilogram. So here's the geometry. We've got the falls. The water comes in at the top and flows down. We're going to choose a closed system, that is to say a fixed mass, a blob of fluid traveling at velocity v1 at the top and traveling at velocity v2 at the bottom. So here's our energy balance. E2 minus E1 is Q minus W. If we can find the heat Q and the work W, we can solve this problem. All right, what is the heat? Heat is going to be transferred in or out of the system here, depending on the temperature. And we're going to assume that the surrounding water is at the same temperature. So the temperature nearby is the same, the temperature nearby is the same at each instant. So we're going to take, there's going to be no impetus for heat transfer, so we're going to take the heat transfer to be zero. That takes care of this term. What about the work? Work is defined to be the integral of pressure integrated over volume. I'm going to slash V for volume so we can keep it straight from velocity. But we're told that the fluid is incompressible. That is to say that the volume is constant for my blob of fluid. Therefore, d volume is going to be zero and the work will be zero. If the work is zero, then this term is also gone, and so E2 minus E1 is going to be zero. That is to say, there's no change in energy as the fluid flows over the falls. That's energy being conserved. All right, that takes care of part A. Let's look at part B. What's going on with internal energy? Well, we're going to take the energy change and break it down. Some of that is kinetic energy, a change in kinetic energy. Some of that is a change in potential energy, and some of that is a change in internal energy. And each of these has units of joules. All right, the left-hand side is zero. Let's write out the right-hand side as each of the component changes here. Kinetic energy change is going to be 1/2 mass times velocity 2 squared minus velocity 1 squared. Potential energy change is going to be mass of the blob of fluid times gravity times the elevation change Z2 minus C1. And internal energy change is going to be mass times little u2 minus little u1. So little u2 has units of joules per kilogram, big U has units of joules. We can cancel the mass for each of these guys. We're going to assume that we have to, for a closed system, that the mass is fixed. We're assuming that the velocity is the same, so this term here cancels, that's zero. We could, I guess, choose a place in the river where the velocities were the same, and let's work this out. I've got 0 equals gravity times Z2 minus C1 plus U2 minus U1, or I could solve for what I'm asked to find, U2 minus U1. That's going to be minus gravity times Z2 minus C1. We can put some numbers in. U2 minus U1 is going to be minus acceleration of gravity, which is 9.81 meters per second squared. Then I've got Z2 at the bottom is 0. Whoops, stop that. Z2 at the bottom is 0. And then at the top, it's 167 feet. Let me convert that to meters by dividing by 3.28 feet per meter. And when I turn the crank on that, I'm going to get a minus, and a minus is going to give me a plus 499 meters squared per second squared. What's that about? Let's look at the units for a minute. Meters squared per second squared. If I multiply that by a kilogram divided by a kilogram, and then if I group that as, let me leave I take a kilogram and a meter and a second squared as one group, and then what's left is a meter upstairs and a kilogram downstairs. Well, this bit here is a Newton. I'm going to have newtons times meters per kilogram. How is that a Newton? Well, F equals ma. I've got a mass here and I've got an acceleration there. Together that makes a Newton. All right. And that a Newton meter is a joule. So now I've got joules per kilogram. So I could write this as joules per kilogram. All right. We would be done. That's what we're asked to find, the delta E. So I could stop here. Let me go a little bit farther. Later we're going to learn that a change in internal energy for a liquid is related to a change in temperature through something called the specific heat, CV. And then for water, the specific heat is about 4,200 joules per kilogram per Kelvin. And again, this is specific heat. And we could take this and we could solve for the temperature change. Temperature is going to be the change in internal energy divided by the specific heat. In our case, we've got 499 joules per kilogram divided by 4,200 joules per kilogram per Kelvin, and that's 0.12 Kelvin. And this was easily measured even in Joule's day. Now the story is that Joule's father was a brewer, and brewers have very accurate temperature devices because they want to get the fermentation temperature correct. Before we leave this, I want to show you an image of Niagara Falls. Here's American Falls in the foreground, the Canadian Falls in the background. Here's the American Falls with a tourist boat called the Maid of the Mist. And here's another view of the Canadian Falls with the tourist boat there. All right, let's do a recap. We're looking for a closed system energy balance of this falling fluid here. And that takes the form of a change in energy is heat minus work. We showed that the heat and work for this case was 0, so the energy has no change in total energy, but that energy could have different forms. We thought about kinetic and potential and internal energy. If we choose the velocities the same, then we just have potential energy turning into internal energy, and internal energy is related to temperature. And now a very large amount of potential energy, this is quite a long drop, 167 feet, a large amount of potential energy produces a small amount of heat energy. And that is one of the reasons that the energy conservation was slow to be accepted. And if you remember that, then all will be well.